It is generally not permitted to have a single-phase conductor in a raceway, as this can create an unbalanced load in the system and increase the risk of overcurrent and voltage drop. In the situation presented, the 3 metal pipes should be run in parallel, with each pipe containing one phase conductor. The grounding conductor should be sized according to the following formula: equals open parenthesis 1.73 times I close parenthesis divided by E, where is the cross-sectional area of the grounding conductor in square inches, I is the maximum allowable fault current in amps, and E is the voltage to ground in volts. The maximum allowable fault current is determined by the rating of the circuit breaker or fuse protecting the circuit. For a 15 kilovolt circuit, the maximum allowable fault current is typically 10,000 amps. The voltage to ground is 15 kilovolts. Substituting these values into the formula, we get equals open parenthesis 1.73 times 10,000 close parenthesis divided by 15,000, which equals 1.15 square inches. Therefore, the grounding conductor should be sized at least 1.15 square inches. When dealing with electrical installations, safety and code compliance are paramount. Firstly, concerning the legality of running a single-phase conductor in a raceway, electrical codes such as the National Electrical Code, or NEC, typically require that all phase conductors and, if used, the neutral conductor of a circuit must be run together in the same raceway or cable. This requirement minimizes impedance and reduces the risk of inductive heating and voltage drop. The presence of a single-phase conductor in a raceway can lead to an imbalance in the magnetic fields, which can induce currents in the metallic raceway. This induced current can cause heating and energy loss, and it also increases the risk of electrical faults and fire hazards. In high-voltage applications, the consequences of such imbalances can be even more severe. Therefore, running conductors in parallel with each phase conductor in a separate raceway is a common practice to mitigate these issues. Secondly, when sizing the grounding conductor, several factors need to be considered. The formula provided, I equals open parenthesis 1.73 times I close parenthesis divided by E, while seemingly straightforward, has underlying principles that must be understood to ensure accurate application and safety. The variable I represents the maximum allowable fault current, which is the highest current that the grounding conductor may be expected to carry during a fault condition. This value is directly related to the protective device, such as a circuit breaker or fuse protecting the circuit. The fault current rating of these devices determines the maximum current the grounding conductor must be able to safely handle without overheating or failing. The variable E represents the voltage to ground, which is the voltage between the phase conductor and the ground. This value is crucial for calculating the impedance of the grounding path and determining the required cross-sectional area of the grounding conductor. The factor of 1.73 in the formula is derived from the square root of 3, which is used in three-phase calculations. However, its presence in this formula might be misleading if the application is strictly single-phase. In a single-phase system, a more appropriate formula might be A equals I divided by a constant that takes into account the conductor material, temperature rating, and allowable voltage drop. When calculating the size of the grounding conductor, it is important to refer to the relevant tables and guidelines provided in the NEC or other applicable electrical codes. These tables provide minimum conductor sizes based on the size of the overcurrent protective device. For instance, NEC Table 250.122 provides guidance on sizing equipment grounding conductors for alternating current circuits. These tables take into account the ampacity of the ungrounded conductors and provide corresponding minimum sizes for the grounding conductor. Additionally, it is essential to consider the material of the grounding conductor, whether it is copper or aluminum, as the ampacity and resistance characteristics differ. Copper is generally preferred due to its lower resistance and higher conductivity, but aluminum can be used to size appropriately to meet the code requirements. For a 15 kilovolt system, the grounding conductor must be sized not only to handle fault currents but also to provide a low impedance path to ground. A low impedance path ensures that the protective device is tripped quickly during a fault condition, minimizing the duration of the fault and reducing the risk of damage to equipment and injury to personnel. Furthermore, the grounding conductor must be properly connected to the grounding electrode system, which typically consists of ground rods, ground plates, or underground metallic water pipes. The grounding electrode system provides a direct connection to the earth, ensuring that fault currents are safely dissipated. The resistance of the grounding electrode system should be as low as possible, ideally below 25 ohms, as specified by the NEC. Regular testing and maintenance of the grounding electrode system are crucial to ensure its effectiveness. Soil conditions such as moisture content and soil composition can affect the resistance of the grounding electrode system over time. Therefore, periodic testing using methods such as the 3-point fall of potential test should be conducted to verify the integrity of the grounding system. In addition to the NEC, other standards and guidelines may apply to the design and installation of grounding systems, particularly in specialized applications such as industrial facilities or data centers. These standards may provide more stringent requirements for grounding and bonding to ensure the reliability and safety of electrical equipment. When running conductors in parallel, it is essential to ensure that all parallel conductors are of the same length, material, and size. This ensures that the current is equally distributed among the conductors, preventing overloading and overheating. Each parallel conductor must be terminated in the same manner, using connectors and terminations that are rated for the specific conductor size and material. The NEC provides specific requirements for paralleling conductors in section 310.10. These requirements address issues such as conductor ampacity, termination methods, and overcurrent protection. In summary, the legality of running a single-phase conductor in a raceway is generally not permitted due to the risk of unbalanced loads, induced current, and overheating. Running conductors in parallel with each phase conductor in a separate raceway is a common practice to mitigate these issues. The grounding conductor must be sized according to the fault current, voltage to ground, and applicable electrical codes. Proper installation, testing, and maintenance of the grounding system are crucial to ensure electrical safety and equipment protection. When working with high-voltage systems, it is always recommended to consult with a qualified electrical engineer or electrician to ensure compliance with all applicable codes and standards. The grounding conductor's purpose is to provide a low-impedance path for fault current to return to the source. This low-impedance path facilitates the rapid operation of overcurrent protective devices, such as circuit breakers or fuses, which disconnect the faulted circuit, minimizing damage and preventing hazards. The size of the grounding conductor is critical for ensuring it can safely carry the maximum fault current expected during a fault condition. If the grounding conductor is too small, it may overheat, melt, or even vaporize under high fault current conditions, rendering it ineffective and potentially creating additional hazards. The formula equals open parenthesis 1.73 times I close parenthesis divided by E provided is a simplified representation and might not be universally applicable. A more accurate approach involves consulting specific tables and guidelines in the NEC or other relevant electrical codes. These tables provide minimum grounding conductor sizes based on the size of the overcurrent protective device protecting the circuit. For example, NEC Table 250.122 specifies the minimum size of equipment grounding conductors for alternating current circuits. The table considers the rating of the overcurrent device and provides corresponding grounding conductor sizes based on the conductor material, such as copper or aluminum. When using aluminum conductors, it's important to note that they have a lower conductivity than copper, so a larger size may be required to achieve the same level of performance. Additionally, the grounding conductor must be protected from physical damage and corrosion. It should be installed in a manner that prevents it from being accidentally cut, broken, or exposed to corrosive environments. If the grounding conductor is exposed to physical damage, it may lose its effectiveness, compromising the safety of the electrical system. Corrosion can also degrade the conductivity of the grounding conductor, reducing its ability to carry fault current. Therefore, it's essential to use appropriate materials and installation methods to protect the grounding conductor from these hazards. The grounding conductor should be connected to the grounding electrode system, which provides a connection to the earth. The grounding electrode system typically consists of ground rods, ground plates, or underground metallic water pipes. The resistance of the grounding electrode system should be as low as possible to ensure effective grounding. The NEC recommends a maximum resistance of 25 ohms for the grounding electrode system. Regular testing and maintenance of the grounding electrode system are essential to ensure its continued effectiveness. Soil conditions, such as moisture content and soil composition, can affect the resistance of the grounding electrode system over time. Therefore, periodic testing, using methods such as the 3-point fall-off potential test, should be conducted to verify the integrity of the grounding system. In addition to the grounding conductor, bonding conductors are also used to connect non-current carrying metal parts of equipment and enclosures to the grounding system. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The size of the bonding conductors is also specified in the NEC, and it's important to follow these requirements to ensure effective bonding. In summary, sizing the grounding conductor is a critical aspect of electrical safety. The grounding conductor must be sized to safely carry the maximum fault current expected during a fault condition. The NEC provides specific tables and guidelines for sizing grounding conductors, and it's essential to follow these requirements to ensure compliance and safety. Proper installation, protection, and maintenance of the grounding conductor and grounding electrode system are also crucial for ensuring the continued effectiveness of the grounding system. When dealing with high voltage systems, it's always recommended to consult with a qualified electrical engineer or electrician to ensure compliance with all applicable codes and standards. The formula provided previously is a simplified version. A more detailed and accurate approach involves consulting the National Electrical Code and utilizing the tables provided for grounding conductor sizing. These tables take into account the rating of the overcurrent protective device and the type of conductor material used. The NEC provides specific guidelines in Article 250 concerning grounding and bonding. Table 250.122 is particularly relevant as it outlines the minimum size of equipment grounding conductors for alternating current circuits. This table correlates the size of the overcurrent protective device with the required size of the grounding conductor. For instance, if the overcurrent protective device is rated at 100 amps, the corresponding minimum size of the copper grounding conductor is 8 AWG according to Table 250.122. The size of the grounding conductor is determined by the ampacity of the circuit conductors and the type of overcurrent protection used. The grounding conductor must be capable of safely carrying the maximum ground fault current that could flow in the event of a fault. If the grounding conductor is undersized, it could overheat and potentially cause a fire or other hazards. The grounding conductor serves as a low impedance path for fault current to return to the source, allowing the overcurrent protective device to quickly trip and to energize the circuit. This rapid response minimizes the duration of the fault and reduces the risk of damage to equipment and injury to personnel. In addition to following the NEC guidelines, it's important to consider the specific characteristics of the electrical system and the environment in which it is installed. Factors such as the presence of corrosive substances, high temperatures, or mechanical stress could affect the performance and longevity of the grounding conductor. In such cases, it may be necessary to use special types of grounding conductors that are designed to withstand these conditions. For example, in corrosive environments, a copper conductor with a corrosion-resistant coating may be used to protect it from degradation. In high-temperature environments, a conductor with a high-temperature insulation rating may be required. It is also important to ensure that the grounding conductor is properly installed and connected. All connections must be tight and secure to ensure a low impedance path for fault current. The grounding conductor should be protected from physical damage and should be routed in a manner that minimizes the risk of accidental contact or damage. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be checked periodically to ensure that they are tight and free from corrosion. The resistance of the grounding system should also be tested to verify that it is within acceptable limits. If the resistance is too high, it may indicate a problem with the grounding connections or the grounding electrode system. In such cases, corrective action should be taken to improve the grounding system. When working with high-voltage systems, it is essential to follow all safety precautions and to consult with a qualified electrical engineer or electrician. High-voltage systems can be extremely dangerous, and improper grounding can lead to serious injury or death. Therefore, it is important to have a thorough understanding of grounding principles and to follow all applicable codes and standards. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. The legality of running a single-phase conductor in a raceway is generally not permitted due to the potential for creating an unbalanced load on the system and increasing the risk of overcurrent and voltage drop. Electrical codes, such as the NEC, typically require that all phase conductors and, if used, the neutral conductor of a circuit must be run together in the same raceway or cable. The imbalance in the magnetic fields created by a single-phase conductor in a raceway can induce currents in the metallic raceway, leading to heating and energy loss, as well as increasing the risk of electrical faults and fire hazards. Running conductors in parallel with each phase conductor in a separate raceway helps to mitigate these issues by ensuring a balanced distribution of current and minimizing the potential for induced current. Sizing the grounding conductor involves several factors, including the maximum allowable fault current, the voltage to ground, and the applicable electrical codes and standards. The NEC provides tables such as Table 250.122 that specify the minimum size of equipment grounding conductors for alternating current circuits based on the rating of the overcurrent protective device. The grounding conductor must be capable of safely carrying the maximum fault current expected during a fault condition, and it should be protected from physical damage and corrosion. Proper installation, testing, and maintenance of the grounding system are crucial to ensure its effectiveness in providing a low-impedance path for fault current to return to the source, allowing the overcurrent protective devices to trip quickly and de-energize the circuit.